All right. The lights are gonna dim for a second. Let's see. Go. Okay. That's a little better. Okay. So let's take a look here, guys. This one I made a little more complicated than I wanted to. I think I made this question before I changed my matrix, but we'll see if anybody got an answer here. So this is even more good timing as far as the review. Okay. So the notation here gets a little strange, and I'm sorry in communicating with you about this. I said this C is the collection of independent column vectors. R is the collection of independent row vectors. So it's just vectors, yes? If I took all linear combinations of the elements of C, I would get the column space. And very quickly, if this is going to have an answer, AX equals B, right? Can anyone tell me what must be true about the vector B? It has to be in the column space. So if the column space is everything that the columns are able to create, then the B element has to be an outcome of some linear combination of those vectors. Okay, how are we doing so far? Okay. So I think this one I made before I decided to change my matrix, so I got a little crazy. Now, again, in the early going, I'm making some of these pretty obvious. How many columns of A are linearly independent? You can just not even look at the reduced row echelon form, and you can just see from the beginning. So obviously the first column vector is automatically independent because you haven't seen any of these. Okay, guys. There's nothing for it to be dependent on because he's the first dude in line. So it's automatically every matrix A is at least got a rank of 1. Yes? The second column, you hit a snag immediately. Yeah, poor little dude's double the first. So that doesn't get added into our column space. It's not independent. What about the third column? Let me ask you this. First column, independent. Second column, a multiple of the first. So how many true vectors do I have so far? I just have 1, correct? So any 2 vectors, the only way 2 vectors can be dependent is if one is a multiple element. So when I get to the third vector, is it a multiple of the first? It's automatically independent. But now things get more complicated, especially the matrix bigger, because now I have 2. So if the third one could be any combination of those 2 I've got so far, yes? Now some of you guys realized that if you add all of them together, the first column, the second column, the third column, you get the fourth column. Since the second column is twice the first, I could also say 3 times the first column plus the third column is the last one, yes? Okay, I like it. Stop for a minute. Okay. Now, so how many columns are there? 2. So what's the rank of A? Let me just jump to there. 2. All right. So the rank of A really just means how many linearly independent columns. If I have 2 linearly independent columns, how many linearly independent rows will I have? 2. Those are always the same. So the rank of the column of C, the column matrix, the matrix of independent column vectors, will equal the rank of the row collection of vectors. Okay. So when I said identify C, I just make a column, make a matrix, and put the independent columns into it. So what do you guys get for C?
1, 2, 0, 3.
Oh, no.
Oh, for B?
For B, yeah.
1, -1, 2, 5.
Yeah, the first column, and then the
4, 2, -1, 1.
third column. Kick ass. Now, what I wanted to point out to you, and I tried to point this out to a point group and they immediately agreed. Couldn't I have made this last vector dependent, but like this? I make this last vector 52 times this minus 37 times this. Yes? Couldn't I have done that? Would that have been as easy to tell on site?
No.
No. So, dear God, there's so many things we're going to do in this class, and we're going to go, oh my God, is there an easier way to do that? And most of the time, a decent amount of the time, yes. Now, obviously, a lot of stuff you just do in the calculator. We are going to do that. I'm not going to make you row reduce a ton of stuff. I might make you do one on the test, little one, just so we all kind of know what goes into doing it, but we're going to grab that from the calculator because we got a lot of other shit to do with it after that, yes? How are we doing so far? So what I'm about to say is, since I could have made that fourth column any weird-ass collection of combinations of the first and the third, thank the gods, I can just look at the reduced row echelon form, and what tells me where in the original matrix to get my independent columns. The leading ones. So here's why. Do you see how this matrix sets up this vector as the first vector, right? This is 1, 0, 0, 0 is representing this column, yes? And real quick, in the process of row reduction, couldn't I have swapped rows? You with me? If I get a series of zeros here, aren't I going to swap that down? That leads to why the row space, the row, the R is not the same way as C to get it. Okay. So this one says, since that's identified as the 1, 0, 0, 0, this one says twice that one is what was here, and that is true. This one identifies the third vector as 0, 1, 0, 0. You guys with me? So if anything's in this space, that means it's coming from the third vector, yes? I need this to be, so what does this one say? To make the fourth vector, I need 3 of the first one plus 1 of the third one, yes. 3 of these. Same way that this one was double this. Because it doesn't have a 1, it has a 2 here, yeah? Okay. So this is 3 of these, yes? How do I make this? Don't I take 3 of these plus 1 of these? Isn't that how I make 3, 1, 0, 0? So don't I take 3 of the first plus 1 of the third? If I do 3 of the first plus 1 of the third, of course I get this, yes? Now just to reiterate what I said earlier, what am I drinking? Oh my God. If you add these 3, how many people did that? And you got 7. Anybody? I know a few of you did. But do you all agree with me? Since this is double this, I could just triple this and add it to this? That's what that's saying. Triple the first column plus 1 of the third column is how you make this. Okay, let me stop for a minute. So it's really, I need this. Some of you guys have reduced matrices before. You've never looked at it the way we are. We are going deep. Some of you guys, unfortunately, have never really played with matrices too much. And right now, you might be going, so please come see me if you're having some trouble with some things that it makes it sound like I'm like, you should know this. Just come see me. Not a major deal. A little bit, but we can get you caught up. Now, the row space, R, the collection of independent rows. Since I could have swapped 2 rows to get to the reduced form, I can't go back to the original matrix. I can't. And I need this. All I'm doing is I'm adding the like terms to reduce this. If I add this to this, aren't I adding components of a column together? I am creating an entirely different vector. That's why this is not in the column freaking space. This is, because that is messed up. That is just, I just added parts of it to itself. That's not the same vector anymore, you guys. Okay, but it still is something I can interpret. I can still use it. The rows I get from the end result. The row R is just this and this. Oh, let me write it over here. Okay. So the rows are 1, 2, 0, 3, 0, 0, 1, 1. Now, real quick. Do you see if, let me see, is there a quick thing I can do this? Yeah. Can somebody take the first row in R plus 4 times the second row? This is perfect. Take the first row plus 4 times the second row. What do you get? Just tell me, what are the numbers? 1, 2, 4, 7. And isn't that the first row in the original matrix? So here's what I really want you to understand. There are other vectors that could be linear combinations of them would make all the possible rows. These two are what I consider to be the most kind of reduced vectors. They're kind of the most useful. Sort of like, I was talking, this is so weird teaching 281 and 284 in the same semester, but I'm pretty sure in here I was talking about, does this bring back any? So I can create every vector in the xy plane if this is y, this is x. But if I said this was y and this was x, I could still do it. It would just be a little more difficult. Yes? Okay. So this is kind of like the best version of every possible vector I could have put in here. Those two are the best. They're kind of like the most reduced in a way. When you go, did anybody do part E? Did it come out?
Yeah.
Okay. Did anybody just go, oh, we'll do that together later. Screw it. No? Okay. Or you don't want to tell me, it's okay. But multiply those out is not hard, yes? Dear God, you have to know how to multiply these out. I am going to make you do some of that. So it's basically like a dot product between the rows and the columns. So 1 times 1 plus 4 times 0. I'm not going to do the whole thing. 1 times 2 plus 4 times 0. 1 times 0 plus 4 times 1. And do you see how, when I do this, together these are combining, this is taking multiples of these columns and combining them, and I end up getting this full matrix. Because what information does this hold? This is double the first. This is the first one added to the third. That's what information that holds. So when I multiply these together, this is like a set of instructions as to what to do with this to bring that back. And this is our first major factorization of a matrix. So when you first learn numbers, you learn to add them, subtract them, multiply them, divide them, and when you learn how to divide them, you start talking about factorization. So 18 has multiple ways to factor it, yes? So matrices have multiple ways to factor them, and each one has a different utility. And I want to point this out before I forget. One of the niftiest things in this book, and I am getting used to using this as a textbook for this course. It's a little more conversational, but so you have to read the book. If you're not reading the book, you're not getting everything out of it you could. Is this where I want to be? No, this is too much. I want to be back here. Yes. The literal second to the last page. Down here, 6 great theorems of linear algebra. Look at this third one. Dimension of the column space equals the dimension of the row space. That's the rank. So that one we know. And that is one of the 6 big ones. Let me see, what's another one? Oh, now this is coming in our future. Null space. This is coming in the future. What's the word null kind of reference? Say again? Nothing. Yeah, exactly. So that the null space has to do with how big is the collection of answers that make the result 0. Which is part of the reason why I wanted the question like I tried to make it, but I made it a little worse than it had to be. Okay. The other page I was showing you, which I think is more immediately applicable now that I think of it, is all the ways to factor a matrix. CR, first thing. We're going to talk about LU today. Yay! So we'll see what the hell that is. I'm going to try to add to this list why they're useful. Yes? It's one thing to know how to do them and kind of like their definitions and so forth, but why the shit are they useful? That's a great question. What the shit does this do for me? It's a good question. We'll get there. Okay, is everybody cool with that? I'll have to finish that out. If you do multiply those together, you will recreate A. Okay, I love it. This one, I don't know. Did anybody find an answer?
No.
Yes? What'd you get?
-1, -1, -1,
That is interesting. -1, -1.
Could it be multiple ones?
Let's see. You might have got it. Yeah, I wanted something you could see on site, and then I changed the matrix around. So let's see. -5 minus 10 is -15. -1 is negative. Ooh, yeah. -2, -6, -5. Yeah, cool. Good job. So I knew one had to exist. It just wasn't what I had created it to be, because I think I changed one of the columns around, which threw everything off. But that's better than I thought it would be. So that's good job. Thanks, man. You get me saying good job. So sorry, you can't get much food with that. Sorry. Why? Okay, real quick. It makes sense that if I make every element of this 0, then the answer is going to be 0. Yes? There's only one situation where I'm guaranteed that there's only one answer to AX equals 0. And that is if A has full rank. If A has full rank, then it covers the entire space. There's only one combination that can make it 0, because other combinations make other elements of that space. So, if I don't have full rank, then AX equals 0 will have more than just what we call the trivial solution, which is just a matrix of zeros. Okay.
So this one has multiple?
Yeah, this is going to have multiple solutions. Later this semester, we're going to develop, this is why this is a little bit early and I wanted it more observable, but I'm glad you got it. We're going to learn, this is related to the null space. So just to give a little preview. The null space is at least one dimensional. Because do you agree that every multiple of that vector you gave me will also make the answer 0? Does that make sense? If I just double it, of course the answer is going to still be 0, because double 0 is 0. So, does that make sense? So that it's at least one dimension. Now, let me see what you guys think. What's the dimensions of the matrix A? What space does it live in? R what? 4. What was our dimension of, what was the rank? How many linearly independent? What was the dimension of the column in the row space? 2. Do you have any idea what the dimension of the null space should be? 2. So we're going to prove that. But it kind of, there should be some party that kind of makes sense. There's 2 dimensions that actually create all the possible outcomes. The other 2 dimensions that make a full 4 are the null space. It's how big the actual null space is. So there's a plane of answers that make the output 0. And again, everything I just said is a little bit ahead of where we are, but I just want to make that connection. So when we get to null space, you already know what that reference is. How big is the space of vectors that actually makes this become 0? So if I have full rank, if my column space is 4, and my matrix has a dimension of 4, what's my null space? 0. So it's not a line, it's a point. It's the point 0, 0, 0, 0 in this case. Okay, maybe. So again, we still have some stuff to prove with that, obviously, but I just wanted to see if it was a little instinctual about what should happen. Okay. Well, there ain't no instinct in here. All right, I'm sorry. So, now, I should have said something else, but I kind of wanted to leave this open. Okay. One person did show me you did nothing wrong. But did anybody reduce this and not change any rows around? Or did everybody switch some rows? Did you not change any rows around? What'd you get?
I got 2, 1, 4, 0, 1, 17, 0, negative 2, 12.
Oh. You're
Oh,
not
wait,
done
sorry,
in this case, right?
Sorry, that was the one before it.
Oh, okay.
2, 1, 4,
Yeah.
0, 1, 17, 0, 0, 46. Sorry, I was looking at the wrong.
Alright. Now real quick, does that match with anybody else? Alright, let's do this together real quick. If I add row 1 and row 2, I'll get 0, 3, 5. And if I double row 1 and add it to row 3, does everybody see what I'm doing? I'm doubling row 1. 4 minus 4 is 0. 2 plus 2 is 4. Good Lord, if I could read my own writing. 8 plus 14 is 22. Is that look good? Yeah, double row 1. Add it to row 3, yes. Yes, okay. Is everybody with me so far? What's the only thing that's not supposed to be there? The 4, yeah. So, this is weird. I thought it came out better. Did I do this one specifically? Wait. Interesting. Is that the same one? Yeah. Sorry. There it is. That's interesting. Oh. Damn you, Jeff. Okay. Alright. So let's do all this together. You ready? This is a beautiful example of, let me see if I didn't get this from somewhere else. This is one we did before. No, okay. I don't know, okay. So, you guys are beautiful. You're all lovely people. I wanted this to be a positive one. That'll just make things a little bit nicer. Alright. So let's do this again. Okay. I'm gonna make some clean paper here. Alright. We're all gonna get through this. I don't like that as much as you do. So real quick, if I do this again, I would take, let me be really specific about what I'm doing. I'm going to take row 1 plus row 2 and put the answer in row 2. Is that cool? So I'm going to do the same thing here that I got before. Now that that's plus, I'm going to take, let me just do this one step at a time. Now I'm going to take negative 2 row 1 plus row 3 and put the answer in row 3. Is that okay? This is what I would make my pre-calc students do. I have no idea if when you took pre-calc, if your teacher did matrices with you. They were supposed to, just to let you know. Okay. If you're like, well, that's too long ago, I understand. So then if I do negative 2 row 1, this would be negative 4, negative 2, negative 8. Negative 4 plus 4 is 0. Negative 2 plus 2 is 0. Negative 8 plus 14 is 6. So that's one nice thing about this matrix specifically is you get there a little quicker. Yes?
Wait, why'd you do negative 2 on the first row?
I changed that last row's 4 to positive 4. See that? I wanted this to be positive. This is just real quick side note. It's annoying as shit to build matrices in Microsoft Word. So I just forgot to delete the negative because I copied a row and put it down there, if you know what I'm saying? And that doesn't help us out, but oh well. So I wanted that to be a plus. And one reason is I only wanted it to take 2 operations to get there, so I can look at this a different way, easier. Let me stop for a minute. So now does it make sense? Because I want to make a 0, so I kill that letter. Okay. This is upper triangular. So upper triangular means 0's in the low, numbers in the high. Now, if you happen to have a 0 up here that just came out of your work, you're fine. That doesn't mean you did something wrong, but you focus on zeros down here and let whatever the hell happens up here, you let it happen. Okay. Now, let me ask you this. Okay, we're gonna go on a wild trip here. And like that's all we do, and I've got like 10 minutes. Beautiful. Okay. Is everybody with me so far? Okay. If this was, let me see if I can build this up. If this was supposed to be a part of an equation, I'm just gonna make that C instead of B because I got a big ass B there. Is that cool? So AX equals B and then get a BX equals C. Same idea. If this was supposed to be part of an equation, I should have augmented this, and then the answer would have shown up. I could have then back substituted. Is that all right? So when you do this upper triangular, dude, and you have an actual answer at the end, you can back substitute. We did that last time, if I remember correctly. You guys keep me honest. I'm pretty sure we did. You never know with me. Do you want to do an example real quick? Because I have tons of time. Okay. So very quickly. All right, listen. You all know how to eliminate. You could do that all day, yes? So let's say I have this matrix, and it doesn't even matter, blah, 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 okay? And I get it down to upper triangular form. Like that, yes? What does this last equation say? And when in doubt, this is x1, x2, x3. So 6x3 equals 6. Therefore, x3 is 1. What's the second thing say? 2x2 plus 5x3 equals 1. Do I know what x3 is? Yes. So 2x2 plus 5 equals 1. 2x2 equals -4, x2 equals -2. Do you guys see what's happening? Wouldn't exactly the same type of thing happen with the first equation? 3 unknowns, 2 of them I know. Do you guys see what that is? That's, I call that dominoes. Not the pizza, but the little things that if you click one, they all fall. So if I get if I get lower zeros, so upper triangular form, that last row is solved. I just divide by the pivot. What are the pivots in this matrix? Just to bring that word back. 1, 2, 6. What's a bad number to have in a pivot? 0 for 2 reasons. The most immediate reason is if I had 0, 0, 0, 6, I'm supposed to divide by 0, and everybody knows when you divide by 0, bad things happen. Somebody in the next town dies every time. Don't do it, kids. Okay, randomly. Okay. Is that okay by itself? That is the immediate usefulness of upper triangular form. You don't have to do full Gaussian, and the rest of it's pretty easy. Now, just to get this in your heads, this class straddles the boundary between mathematics and computer science. Several of you guys have already said you want to go into machine learning, you want to do that kind of thing. Some of you guys probably want to do some other computer science related stuff. Some of you guys are like, I just want to do, I don't even know why I'm here. Oh, all right, that's fine. I've got all your majors in the survey. That's most of you guys filled out. I think some of you guys are engineering. Is that true? Anybody engineering? Yeah. Yes. Okay, that's another big contingent. So even engineering, you're going to have matrices that deal with transformations of things. They might be within computer programs, but then as a human, you have to be able to interpret what the hell it's doing. Yes? Okay. So every time we do something like this by hand, we have to also consider how long it would take a computer algorithm to do it. And when I create a computer algorithm, it's got to be able to handle multiple situations. In fact, it's got to be able to handle every situation I can give it, correct? So anybody have done any computer programming in here? Can you guys tell me anything about sorting methods? Sure, sorting methods. How do you determine which one's best or which one's better? I don't need a whole treatise on this, okay? But does that question evoke immediate answers in your head? Okay. So basically in sorting methods, you talk about what it takes on the order of, how long it takes the sorting method to work. So you can say it's on the order of n, on the order of n squared, on the order of n cubed, on the order of 1/2 n cubed, whatever the shit. So n being the number of entries in your array, Are you guys all with me a little bit? Okay, good. So, I wish I would have done more computer science, but I did some, but not as much as I wanted. It's too bad for me. Okay. All right. That was a huge tangent. Is that cool by itself? So that is the immediate usefulness of upper triangular form. But computer-wise, this is lengthy, especially if the matrix gets much bigger. The length of time goes up by quite a bit. And if your computer program has to do that kind of thing a billion times, now you're talking about this thing taking way too much time. You need a very efficient method. So, 5 minutes. Let me see. Okay, I'm going to do this last little bit. I forget if I said I was going to do something else. Too bad. I'm going to do this last little bit. I want to capture the two things we just did in a matrix form. Okay. So, for example, what matrix would represent taking row 1, adding it to row 2, and putting the answer in row 2? So again, if I start with 1, 0, 0, 0, 1, 0, 0, 0, 1, you can literally do what I just said. And that matrix would be a command that if you multiply another matrix by it, it will do that. So this is what I said last time about elementary matrices are a series of little subroutines that and if you combine all of them, it's one big subroutine that does the same thing to every matrix it attacks. So what would that be? I'm sorry, I cut you off. So if you take row 1 plus row 2, if you take row 1 plus row 2 and put the answer in row 2. Add row 1 to row 2. Right here. 1, 1, 0. And if I leave the other two rows alone, the only thing this matrix does is if I multiply it by any other matrix, especially the right one, there you go, Jeff. If I multiply these together, I'm going to get what we got here. Okay, we stop for a minute. Because this little list of instructions does the same thing that multiply by this matrix does. What did we then do? So I'm going to call this one, what do I call this one? I'm going to call this one E21, because I want to. Because didn't it do row 2 and row 1? Okay. What did I then do to the result? So if you do this, you can kind of verify this. If you multiply these together, you get the same thing we just got up here. So now I want a matrix that does this. -2 row 1 plus row 3. So if I take row 3 and I subtract 2 row 1s and I put it in row 3, what does that look like? Take row 3 and subtract 2 row 1s. Sorry, 2 1? Yes. Take row 3 minus 2 of these. What do you get? -2, 0, 1. So this matrix will now just do that one thing. It will take twice row 1, take that away from row 3, and put the answer in row 3. That's what this little program says. This little program here. So if I attack this with that, I will get back to, my God, Jeff, this is taking forever. I know. I'll get back to the result from earlier. 214, 035, 006. Now, real quick. If I multiply these two together, these two, if I multiply those two together, I will get one matrix that does both things. I've got to multiply them in the correct order, though. Which one did I do first? E21. So if I have to multiply E31 times E21. And what did we do? We applied that to A, and my result was, what letter do you think I would use to represent this guy?
U.
No way. Get out of my head. Now, the whole thing we haven't even talked about yet are inverses of matrices. And that's what I'm going to just focus on next time after the quiz. Remember, we have a quiz on Wednesday. Yes. If I took the inverse of these two, and by the way, the inverse of these two, let me see if this makes some sense. it doesn't just invert the matrices, it inverts the order they act in. Because when I go to undo something, don't I undo the last thing I did first, and then I undo the first thing I did, if I only did two things? So here's what's really neat. This matrix, so if I apply this to both sides of this, I get A equals E21 inverse E31 inverse U. Now, right now, that doesn't mean shit to you. I understand. I know. We haven't even talked about how to make a inverse yet. I understand this shit. But here's the next natural way to factor a matrix. We're going to do it like math people always do. We're going to do it a long-ass way, and then I'll show you a shortcut. Shortcut's still a little long. It's okay. We're going to make it. We're going to make it. If you got into Math 24 and you didn't think some of the works would be long, you should have. Incorrect expectation. All right, guys, that's enough. So next time quiz, I'll have a practice test. And whatever you get through this Wednesday is what's going to be on the next test. So we might not get through all of chapter 2. Woo!
Do you have a stapler?
Yeah.